relation which is reflexive, antisymmetric, and transitive. Is a relation that is reflexive, antisymmetric, and transitive. And I'll briefly say what this a relation means. For example, I have the set X, any subset of X cross X is what a relation is, and I will say this is the relation. Relation can be ordered pairs. If an ordered pair AB is in the relation, I will write that A is less than or equal to X. That is the notation. A is less than or equal to B. So instead of saying A is less than or equal to B, I say AB is in the relation less than or equal to, in that sense. Okay, so basically, what does it mean? That is X less than or equal to is called a partially ordered. That is less than or equal to is called a partial order on X. If I have the following, one is that X is less than or equal to X, there is a reflexivity for every X in X, and 2 is X is less than or equal to Y and Y is less than or equal to X actually means X equal to Y. It is what I mean by anti-symmetric. Okay, if you have X less than or equal to Y and Y less than or equal to X, I want X equal to Y. Of course, less than or equal to in ordinary, real number system actually has these properties. I'm imitating those things. Let us say this less than or equal to is an abstract one, some relation, and transitivity, which says that X is less than or equal to Y and Y is less than or equal to Z, implies X is less than or equal to Z. If these properties are satisfied, I call less than or equal to a partial ordering, and we call X together with this inequality we just introduced, okay, with the ordering that we have just introduced, and we call X less than or equal to a partially ordered set. Sometimes I might just say poset. I don't say poset, but that's also a poset. I'm not so much used to say poset. I say a partially ordered set. Okay, so in case any two elements in a partially ordered set are comparable, then you say that partial ordering is a total ordering. Okay, less than or equal to is called a total ordering, or maybe X less than or equal to is called a totally ordered set, or a simple ordered set, or a chain is called a totally ordered set or a chain if every pair of elements in X are comparable. If I take any two elements X and Y, I must have either X is less than or equal to Y or Y is less than or equal to X. There is no other option. Definitely they should be comparable. You can take an example like this. So let's say this is A and this is B, C, D, E, F. As you go up, is that A is less than or equal to A is less than or equal to C, B is less than or equal to C, C is less than or equal to D, D is less than or equal to E, D is less than or equal to F. And there is no relationship between A and B. So I can have such a relationship. So on the set X consisting of A, B, C, D, E, and F. Okay, I think I have inequality described by this thing. As I go up, the object becomes bigger in that sense. But A and B are. Kiran Kumar, can you see it now?
Yes, sir.
So I said what a set is now. we call x less than equal to we call x less than equal to that a partially ordered set, and a partially ordered set is called a totally ordered set. Okay, right? A poset x. I have only little room, so I said poset. A poset x less than equal is called a totally ordered set if or a chain. If every pair of elements of x, uh, if every pair of elements of x are comparable. We talked about a lot of things last time. Something like it. I can talk about given a subset A of x, I can talk about upper bound. Okay. Um, if A is a subset of x, if A is a, let A be a subset of x. Yeah. Uh, we say x naught in A. Yeah, maybe I can even. Yeah, we say an x naught in x. Oh, I think I should be a little careful when I want to say upper bound. Um, an element of x naught can be bigger than or equal to every element of A. Uh, then I can say that is an upper bound of the elements of A. But that upper bound need not be in A. Okay, but if that upper bound is in A, right? Okay, let me maybe not worry about it. Introduce what is called a maximal element. Okay, we call A in A or maybe A naught in A is a maximal element of A. If of capital if there is anything that is bigger than or equal to A naught, that has to be in A. Okay. If uh, for every x in uh, it's a maximal element, so I don't have anything bigger than that in A. So anything I take in A, I cannot say it's less than equal to that. Anything, yeah, anything in A is, yeah, if for every x in A is less than equal to x uh, implies x is A in that sense. That's a maximal element. Okay, right? There's nothing beyond that. If anything is in A, which is bigger than equal to A, it has to be A only. Okay, so in that sense, I see, for example, um, yeah.
A not,
Um, it
A
has to
not.
be, okay, you're right. A naught in A is a maximum element of A. For every x in A naught is less than equal to x implies x equal to A. That's what I mean by maximum. Similarly, you can talk about a minimal element. I think you understand that. Okay. Uh, B naught in A is called a minimal element if for every x in right, for any x in x is less than equal to B naught implies x has to be B naught. In that sense. What I stated yesterday in the previous class is the following. The so-called Jones lemma, very beautiful. Jones lemma. Jones lemma tells you is very powerful tool in many areas. Okay, it's a theoretical result. It says that in a poset, in a partially ordered set, if every chain has an upper bound. Upper bound means there is an element which is bigger than every member of that. Okay, if every chain has an upper bound, uh, then the set has to have a maximal element. Okay, if in a partially in a partially ordered set, in which every chain has an upper bound. If every chain has an upper bound, then uh, uh, the set has a maximum element. Okay, that is the result. Okay, a partially added set in which every chain has an upper bound. Uh, uh, maybe a partially added set in which every chain has an upper bound has a maximal element. That's it. Has a maximal element. That's what the Jones lemma. I'm not going to prove the Jones lemma. We can actually take it, but that is a separate, discussion. We're not doing all that set theory, but somehow axiom of choice will be used in proving the Jones lemma. And of course, in terms of axiom of choice is equivalent to Jones lemma would imply axiom of choice too. So I'll tell you what axiom of choice is. Uh, okay, we'll use this especially to prove that we are talking about in compactness that if every space is open cover, a topological space, if it's a finite subcover, then the topological space itself is compact. We'll come to that. Okay. Let's talk about axiom of choice. Maybe yeah, why not? Axiom of choice. Okay. Okay. What axiom of choice basically says is that if in the finite case it's very easy. If I have two non-empty sets, the non-empty sets, so I can pick up one element from the first set and one element from the subset. Second set. So I have a pair of elements. First one comes from the first set, second one comes from the second. Indeed, if I have finitely many sets x1, x2, etc., xn, each of them is known to be non-empty. I can choose one element in capital X1, one element in capital X2, and so on, one element in capital Xn. That is obvious. But if they are non-empty set, if it's a non-empty set, I can choose one. Second one is non-empty set, I can choose one. So it looks like it. Now, in general, if I have a collection of non-empty subsets, it's a whole collection of non-empty subsets. It's not a finite collection; it can be uncountable collection. We don't even care what is the size of this indexing set is. I have a whole lot of non-empty sets. Then the axiom of choice says that from each one of them, I can choose one element. So let's see that. If x alpha in delta is a collection of non-empty sets, is a collection of non-empty sets. Okay, we can then there exists a uh, a collection x alpha in delta of elements such that x alpha belongs to x alpha for each alpha in delta. So each one has one non-empty element. I have chosen one. That's what this axiom of choice says. One would say, what's big deal? Everything is non-empty. You have selected one from each one of them. What's big deal? One may say that, but that's not as simple as that. Okay, we will see. I mean, it may look self-evident, yet we would like to take it as as an axiom. It's not where this is going to imply a lot of very some things which are a little difficult for us to accept as it is on the face of it. But if something is proven, to be equivalent to this, then it's equivalent to that. There's no complaint about that. In other words, what is that we are saying that? In other words, we can find a function f from delta to union x alpha in delta such that f of alpha is in x alpha for each alpha in delta. Is that what you're saying? So I can create a function from the indexing set to the union of all x alpha. So that for each alpha in the index set, f of alpha is an element of x alpha. Actually, such a function sometimes we call the choice function for this family. Okay, I will rewrite in another way. So I'm going to write in another way. In other again, let C be a collection of non-empty sets. Each set is a non-empty set. Then what we are saying is that then there exists a function f from the collection itself to the union of all members of that collection. So the collection itself is taking an indexing set, that's what it is. For each member of the collection, I can choose an element in that. Okay? There exists a function fc from to that such that f of a is in a for each a in c. Isn't that what it says? Right? So the collection has lots of uh, sets in it, and the collection is indexed by the collection itself. Here, I have indexed this collection by some delta. For each alpha in delta, there is an x alpha, and all these x alphas are in this collection. So the same way C is a collection of sets. Each set is indicated by itself. So for each set C in the collection, that C is a non-empty set, and that non-empty set has an element in it, and that element is your f of a. Okay. See, what happens is that even though you can say there is such a function, you probably constructing such a function is not very clear. For example, here itself there is an indexing set. So for each alpha, I choose one. Which one did I choose? I cannot really prescribe a procedure in which I can choose it. Only in specific cases I can do that. Otherwise, I cannot prescribe the procedure in which I can choose the element a small x alpha in capital X alpha. Because of the lack of that procedure, it's not very clear what the function is. But existence of the function is guaranteed by the action of choice. Okay. Also, we've been doing it already several times. This product of all x alpha, alpha in delta, for example. What does this contain really? It contains really some family like this, X alpha, alpha in delta is a family in it. This is a member of that. That means small x alpha belongs to capital X alpha for each alpha in delta. So in other words, you're saying that this entire product has at least one element. So this is non-empty. Why this is non-empty? It has many, many elements anyway. That this is non-empty is what action of choice is saying. In other words, or equivalently, if x alpha is non-empty uh, for each alpha in delta, then the Cartesian product by x alpha, alpha in delta is non-empty too. That is what we are saying action of choice. We will actually use action of choice to prove John's lemma. Okay, action of choice will be used to prove John's lemma, and I will use John's lemma to actually maybe I'll develop this. I'll prove John's lemma to prove what is called well ordering principle. I'll tell you what it is. Well ordering principle. As a matter of fact, all these things are these two are identical. I think all these things are equivalent. Okay. Okay. So let's talk about what I mean by well ordering principle. Okay. If you take a set of all natural numbers, set consisting of 1, 2, 3, etc. Okay, every subset has the smallest element. In it, the whole n has the smallest element. One is the smallest element. Okay, right? But if you look at all real numbers, not every subset of R has the smallest element. The only lower bounds may be there. No, lower bounds also need not be there. Okay. So not every subset has the smallest element. Here, for example, there is no guarantee that the sets have largest elements, but every subset has the smallest element. So um, indeed, the whole space need not have a smallest element. In this case, it has. Even if the whole space has a smallest element, there is no guarantee. Uh, for example, if you look at 1 to infinity, okay, the entire set has the smallest element 1, but many subsets do not have smallest elements in them. So what well-ordering principle says is that, well, we'll come to the statement of that. I can introduce a different kind of ordering on it. I can say that somehow introduce an ordering. Okay, I'll say that there is another ordering I will define dashed. I say A is less than equal to B if B is less than equal to A accordingly. If I use that, then I think I know 2 is smaller than 1, 3 is smaller than 2, 4 is smaller than 3, and so on. In that case, there is no smallest element. So I can have various different orderings on it. Some of them will ensure that every subset has a smallest element. Some of them do not ensure that. Okay, so let's start with that. A partially ordered set need not have uh, a smallest element. And even if it has, not every subset of it has to have a smallest element either. Not every subset of it has to have a smallest element. Okay, right? I'll give you some examples. Okay, uh, let's say I can take maybe yeah, let's say W, which is all natural numbers union singleton zero. Okay, that's the W whole numbers, right? With the usual ordering, I think every subset has a smallest element in it. It's a usual ordering. The ordering all of us know. A number is less than some other number. You know what it means. Like 2 is less than 4. 4 is greater than 1. You know, with that ordering, with the usual ordering, omega has every subset of omega has um, is has smallest element. I can introduce a totally different ordering, an omega plus omega. Yeah, why not? An omega plus omega, another example. I can have a lexicographer's ordering, okay, is ordered by lexicographer's ordering. What do you mean by that? It's very obvious, you know. That means for A comma B in maybe for uh, AB and XY in omega cross omega, uh, AB is considered to be less than or equal to XY if either A is less than X, if either A is less than X or A equal to X and B is less than or equal to Y. Okay, if A is smaller than X, this is how the dictionary ordering is. The lexical corpus ordering is a dictionary ordering. In case A comes before X, the entire AB comes before XY. Okay, in case A is equal to X, then the second letter B has to come before Y. Okay, that's lexical corpus ordering. In a dictionary, the words and how are the words written down in a dictionary, right? Those for which the first letter is A are written down first. Those for which the second letter is B are written after all those things, and so on. So out of the A and X, if A is smaller, all the ABs, whatever B you take, all the ABs is smaller than XY. But in case A matches with X, then I want to make sure the second letter B is less than equal to Y. If B is less than Y, you say that AB is strictly less than XY. Then. Okay. You can easily see that according to the lexical ordering, omega plus omega also every non-empty subset in omega plus omega will have the smallest element. Okay, then also then omega plus omega every non-empty subset of omega plus omega will have a smallest element. It's very easy. Okay. Actually, you can just look at the first coordinates and look at the first coordinates are subsets of all the first coordinates will make up a subset of omega, and that has the smallest element. Then I think you can understand what it is. Then you look at all those things for which the first coordinate is that smallest element. You compare them amongst them. The second coordinates look at the smallest one, and that so smallest in the first coordinate, and amongst all those in which that smallest first coordinate is available, the smallest in the second coordinate. That pair will be smaller than everything else. So I have that. But look at this following thing. For AB and XY in omega plus omega, uh, we we say AB is less than or equal to XY if 2A plus 1 by 2 power B is less than or equal to 2x plus 1 by 2 power y. Suppose I wrote this inequality. You can easily see it's kind of a partial accurate. It's not impossible to check that's a partial accurate. Okay, I can verify that. It's a partial accurate. For partial accurate, you need reflexivity. Reflexivity is obvious because this is equal to this. So anti-symmetry. Okay, I think anti-symmetry is also obvious. Is that clear? Because then it becomes an equality. So for example, first of all, reflexivity. AB is less than equal to AB. Why? That's because 2A plus 1 by 2 power B is equal to 2A plus 1 by 2 power B. So there is nothing to prove. Antisymmetry, if AB is less than equal to XY and XY is less than equal to AB, then what happens? Okay, then you get 2A plus 1 by 2 power B is less than 2x plus 1 by 2 power x is equal to 2A plus 1 less than equal to 2A plus 1 by 2 power B. That means these two are equal. So this will tell you that 2A plus 1 by 2 power B equal to 2x plus 1 by 2 power x. And now that's going to tell me 2A plus 1 into 2 power x, excuse me, this would tell you 2A plus 1 into, this is 2 power y currently, that's 2 power y is equal to 2x plus 1 into 2 power a. You see, because 2a plus 1 and 2x plus 1 are odd. So when you see that, if you want these to be equal, 2 power y ought to be 2 power a, that means y equal to a, and 2a plus 1 has to be 2x plus 1, a equal to x. So you can easily prove anti-symmetry. Okay, transitivity is obvious. Is the same thing. So this is a partial ordering. So this is a partial ordering on omega cross omega. And I want to see very quickly that if you really look at AB plus 1 will be less than or equal to AB. Why? Notice. Why? Because, yeah, it's all clear now. Because what does this tell you? 2A plus 1 by 2 power B plus 1. Oh, yeah, that is strictly less than 2A plus 1 by 2 power B, is it not? So in that sense, this is actually strictly less than A comma B. Okay, right? So now you can see that. Now you can see that A B plus 2 is even more than that. A B plus 3 is more. Yeah, A B plus 1 is smaller than that. A B plus 2 is smaller than that. A B plus 3 is smaller than that. Oh, if you go that way, I don't get a smallest element. So it's the same set omega cross omega. I have a different kind of an inequality, partial ordering, according with respect to which this omega cross omega will not have the property that non-empty subsets of it have least elements. So and they know the non-empty sets. So non-empty subsets of omega cross omega need not have smallest elements. Okay. Now, what I'm going to say is, I say a set is well ordered if every subset of it has a um, smallest element. Is the definition of well orderedness. A partially ordered set x less than or equal to is said to be well ordered if every non-empty subset of it has the smallest element. Non-empty subset of it has the smallest element. Okay. See, the R is not well ordered. Well, this is terribly bad. But too many non-empty subsets of it will not have, smallest elements. They just open it all to 0 to 4 has no smallest element. Looking for a smallest element is just meaningless in R, right? What we will show to you is that action of choice and the Jones lemma can be used to prove that on any set you take, any non-empty set you take, you can introduce an ordering so that that becomes a well-ordered set. So this is the theorem. Well-ordered, this is a theorem about well-ordered sets. Okay, well-ordered theorem or something you can say that. I don't know if I have a name for the theorem. Well-ordering theorem. Well-ordering theorem. Every non-empty set can be well-ordered. Every set can be well-ordered. If empty set, what is there? Uh, Empty set will be anyway. There is no need of putting any ordering, and you are all good. Okay, you cannot say that any subset of it has no least element. Then you have to find a subset for which there is no least element, etc., etc. So every set can be well ordered. Every set can be well ordered. Definitely, this is a surprising result. You can have horribly big sets like R already. It's not a horrible. It's a set we keep on using. I should not use the word horribly. But yeah, you can have all sorts of sets. Every set, you can introduce a appropriate ordering on it, with respect to which every non-empty set uh, of it will have the smallest element, which is really kind of a surprising theorem, but that is true. Every set can be well ordered. Okay, I want to demonstrate this by, yeah, maybe we can, uh, yeah, we can prove it easily. There's a proof using John's lemma. Okay. Okay. Now, what I want to look at is I want to look at the suppose W. First of all, take a set. Take an let X be an empty set. Let X be a set. It can be an empty set also. Take it. In empty set, I don't have to prove it. Say like suppose X is an empty set. Okay. Let X be a set. Okay. Hmm? Doesn't matter. I should have it. Let X be a set. Huh? W consists of all well-ordered subsets of X, A less than equal to, where A is a subset of X and less than or equal to is a well-ordering on A. Less than or equal to is a well-ordering on A. Okay, that's very easy. Of course, if X is empty set, okay, then I will take empty set itself. You don't have to write empty relation only, plus empty relation. Okay, and this becomes a well-ordered set. So that's, but if X has some non-empty elements, maybe I just take X in it, and the A consists of that small x, and X is less than equal to X. There is an ordering, and there's a well-ordered set. So I think W will be non-empty. The class of all well-ordered subsets of X will be non-empty. You have bare minimum empty, or maybe okay, or in case X is non-empty, I take one element of X and put that in A and said X is equal to X. That's the ordering. X is less than equal to X. That's the ordering. What non-empty subsets does it have? It itself. And what is the smallest element itself? So definitely W is non-empty. Okay. Then W is non-empty. You know what? In W, I will introduce another relation. Okay. Less than equal to W, uh, we introduce a relation less than equal to W on W. How? For A less than equal to A, B less than equal to B in W, we say A less than equal to A is less than equal to maybe in W, B, B less than equal to, okay, less than equal to B maybe. That's the inequality of B. If, let's stop me if you have a question. I am introducing an ordering in W, okay. What is that ordering? If I take A with its inequality, B with its inequality, this is less than equal to that. When if A should be a subset of B, if A is a subset of B, and A will be a weak initial uh, segment of B. A is less than equal to B, and A itself is maybe uh, it can be a weak initial segment of B, or some A can be maybe a S of B, S of B for some B. in B. Uh, that means I'm trying to also the inequality B restricted to A is the inequality in A. Okay. So I have the same inequality as that of A for the members of A in B. That is less than, if I take two elements and say they are A is less than equal to, if I take two elements A1 and A2 in A, they are actually in B. What do you mean by A1 is less than equal to A2? It means that A1 is less than equal to B, A2. So the same inequality. If that happens, I say this is less than equal to that. Otherwise, don't bother comparing the two things. That's not a problem. Okay. After all, that itself is compared to itself. Why not? We can do that. No, no, no. Okay. So, of course, I can say it's also possible both of them are equal. I will allow that also. Okay. If they're equal, I can say that if either they're equal or maybe if, let's say this, if either A is equal to B along with the inequality. A equal to this or A is contained in B. Okay. A is contained in B, comma, less than equal to B restricted to A is less than equal to A. Actually, it's an inequality, right? So restricted to means restricted to A cross A. Okay, restricted to A cross A, if you want to say that. Is less than equal to A. And this A, which is probably not completely equal to B, is an initial segment SB for some B. That is the inequality. Right? This is what is called a continuation. B is the continuation of A. Okay. So same inequality will be prevailing. Then I can easily show that this is a partial Lagrangian W. Okay. Then less than equal to W is a partial ordering on W. And class of all on the collection of all partially ordered subsets of X. Okay. Now I want to claim very easily, you can prove that every chain in W I show has an upper bound. Take any chain in W. I'm going to show you that every chain has an upper bound. If every chain has an upper bound, the entire W has a maximal element according to Johnson. Okay. And that maximal element you will easily show is really the ordering on X because you can't have anything more than the maximal element. Anything outside, okay, we'll come to that. We'll come to that. Okay. You take any chain in W. I claim you look at uh, C not equal to union A in that chain, and with continuation as the inequality. Okay, continuation will be very easy in this case, C naught. And if I take any two elements, A and B in C naught, they will be, A will be in some A1 and B will be in some A2 for some A1 and A2 in the chain. But chain means any two elements are comparable. So A1 and A2 are comparable. So maybe A1 is less than equal to A2 in this, which actually means I see the inequalities can be shared by these two things. Now, because of that, you introduce the notion of because these are comparable, so this element is in this element is in this, right? So whatever is the inequality, because both of them are in A2. So in A2, whatever is the inequality between A and B, A and B are both in A2. In A2, you have some inequality between these two things. Probably, this is probably what you have. Okay, in A2, maybe A is connected to this. That is what I say the inequality in C0. So how does any two elements in C0 comparable? We take those two elements in C0, they are in C0 means one of them is in A1, other is in A2, but A1 and A2 are in the chain, that means they are comparable, and therefore one of them is smaller than the other. It may be A2, or it may be A1. If A1 is smaller than A2, now A is in A, B is in B, so both of them are in A2, and A2 has a certain inequality between A and B, and that inequality is what I will utilize for the C0. Okay. So that way, I can introduce an inequality and C0. C0 with natural inequalities less than or equal to will become a well-ordered set because any two elements are comparable. I just proved. Okay. Let C0 be this. Uh, there is a natural ordering that can be introduced in C0, the continuation ordering. A natural ordering is there at C0, namely the continuation, namely the continuation. What is that? That is, yeah, whatever I have written here, I'll write that again. Let A comma B belong to C naught. And then there exists AA and AB in C, so that no need to say AA, AB. Let's call it A1. A1, A2 in C, such that maybe A is in A1 and B is in A2. But A1, A2 are in the chain C. C is a chain. C is a chain. A chain means any two elements in that are comparable. Hence, A1 less than or equal to A1, A2 less than or equal to A2 are comparable. If they are comparable, one of them is smaller than the other. Say they're comparable, right? One of them is smaller than the other. So you just figure out which one is smaller. Maybe that one is smaller than the other. It doesn't matter. Say A1 is smaller than A2. Then A and B are both in A2. And there is an inequality. And you will see what is the inequality between A and B. Okay. Uh, right? There is an inequality between uh, uh, A and B. Yeah. A is in A, so yeah. A is in A1, A is in B is in A2. So already there is a even A2 or A2. A2 is already well ordered set, right? Okay. A2 less than equal to A2 is already well ordered. Therefore, there's an ordering between A and B. Hence, there's an ordering between A and B. There is an ordering between small a and b. And I want to take that ordering to be the ordering in C. We take that ordering between A and B as ordering in C. Ordering between A and B as ordering in C. So what I'm saying is that if A is less than or equal to A to B, then we say A is less than equal to according to C naught in B. That is the ordering I have in C. Okay. Now C naught with that ordering I have just introduced in C naught, that you see is a well-ordered set, and that is an upper bound of W, is an upper bound of W. Fantastic. So you proved that every chain in W has an upper bound. Therefore, by John's lemma, thus every chain in W has an upper bound. Therefore, by John's lemma, by John's lemma, W has an upper bound. The W has a maximum limit. So it's a maximum element. W has a maximum element means what? It has some element, starts of some maximal element. Maybe I can call that y comma its own inequality. But okay, y comma its own inequality. I'm going to claim that y has to be x. Okay, say maximal element, say y comma this. So it's very easy to claim that y equal to x. Okay, it is easy to see y equal to x, which means, yeah, finally, x with appropriate ordering is in W, that is, x is a well-ordered set, and we are done. Why is it easy to see that y equal to x? Y is not x. You have one extra element, If y is a proper subset of x, okay, choose some element x in x minus y minus y. Then and introduce a particular ordering and introduce less than or equal to, I can call that not or something, on y union this extra element x. Very easily, all you see that the ordering that is on y is already there. Only x is bigger than everything in y. By declaring x bigger than everything in y, by declaring y is less than equal to x for every y in y. Then that becomes a well-ordered set. But if you take any two elements, if both are in, if you take any two elements in this extension, what is the extension you are doing? Y union x is bigger than y. Okay. In that, if you take any two elements, if both are there and y, always they are comparable. Okay. If something in y and x is taken, then x is taken to be bigger than everything else. So that's comparable. If both are x and x only, then they are also comparable. So what happens? This becomes a well-ordered set with you said this is the maximal element, and you have produced something bigger than that, which is a contraction. Okay. With that, ordering, that ordering y union x is well ordered, contradicting maximality of y, contradicting maximality of y. Beautiful. That's it. That's it. Therefore, as I said, uh, y has to be x. So I have proved that x is well ordered. So every set is well ordered. Of course, it's just a existential proof. It's not. This is a maximal element. This is an existential proof. I cannot tell you easily. It's a good exercise by itself. Why not? is well ordered. How do you well order R? Okay, that will be a good exercise. R is such a big set in this context. R is not a very big set in general, big sets, but I'm saying that in this context, R is very big, Um, and how do you well order that? We have not given you that. We just said that every set can be well ordered. After all,
One question I have here. So we took A in A1 and B in A2, and we defined less than or equal to on C naught as less than or equal to B essentially,
Mhm.
right? Um, but B can, C naught is a union of all A's, but B can be in some other set, A3. Is there some uh, confusion which less than or equal to that I should take as C naught? Like that less than or equal to C naught is unique, is not unique.
Yeah, there wouldn't be a problem. That is from the very definition. It will just, uh, I have to prove that to you, right? So, uh, what I
Uh,
did is I considered C to be a chain. So, if you suppose you have
okay.
taken another A3,
That has to be part of A2. Okay.
yeah,
Okay.
they
It's a
have to have
chain.
a comparison there.
Yeah.
So that forces us to anything you use, it is okay.
Yeah. Yeah. Anything you use, it is okay, or take the maximal of it. If you,
Yeah,
yeah. 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 Makes sense.
that's
Because
why
it
it
is
is
a
not
chain.
each. Even
Yeah.
while discussing this, I just was a little worried. Yeah, but each is a well-ordered set also.
Yeah. Yeah.
So I have a
Uh,
comparison, and because C is a chain, even if you take another A3, and there is no ambiguity in the comparison because A1, A2, A3 themselves has some kind of a relationship between them.
yeah. Yeah.
Mm. Okay, so that's what it is. And that is why action of choice is not considered to be something so obvious. Action of choice has proved that every set can be well ordered. A lot of people thought that's just kind of really maybe a little too much, but it is not. I mean, okay. If we have a chance sometime later on to study as a theory, we'll do that. For the present, I don't want to say more. And, oh, I can prove another wonderful result from, uh, from this well-ordering theorem, or from Johnson. I can, yeah, I have mathematical induction is there. What does mathematical induction say? It's about any subset of natural numbers which has one in it, and every time n is in that, n plus 1 is also in that, then together this will imply that x itself is n. That is mathematical induction. Of course, sometimes you write the induction in a different way also. Complete induction, you say that if S is subset of N, uh, if 1 is in S and 1, 2, 3, etc. N are in S implies N plus 1 is in S, then together these imply that S is equal to N. That is mathematical induction. We can have transfinite induction. I don't need a natural number set. I can just have a well-ordered set and introduce transfinite induction in the well-ordered set. Okay, so let x uh, be well-ordered set. So the transfinite induction says the following: if uh, well-ordered set and uh, S is a subset of S, S is a subset of X that satisfies, okay, the following is that satisfies set such that set in a subset of X such that, okay, for every X in S, entire initial segment of Sx, okay, Sx, initial segment of X, weak initial segment, no, just initial segment of X means all the elements which are smaller than X, okay, uh, is contained in S for each X in S, okay, then S is equal to X, okay. uh, that's what the transfinite induction is. Proof. If S is not X, I'm going to choose an element which is outside. Okay, if S is not an X, choose an element X in X minus S. Okay. Oh, well, then X minus S is non-empty. That's good enough. All I need is I don't need that. Then X minus S is non-empty. But every non-empty set, because X is well ordered, every non-empty set has, the smallest element. Huh? Let X be the smallest element of X minus S. That's the smallest element. So anything smaller than that will not be in that anymore. Therefore, Sx is contained in S. Okay? But S has the property that then X has to be in S. The property S has. S is such that Sx is in S. What is S? So such that Sx is in X. No. I didn't write it properly. Okay. Such that for every X, okay, such that for every X in X, Sx is in S implies X is in S. Yeah, I did it. Very close. Okay. Transfer direction is what? S is such a, if S is a subset such that for every X in S, the initial uh, uh, segment Sx is contained in S, then X has to be in S. Then S has to be S. Okay. So therefore, X is in S. But that's a convection. Okay, because X is after all outside that. It's a convection. So you can see that I have uh, some kind of a generalization of induction in a simple analysis, basically. Hmm? It's a convection. Therefore, S has to be X. Clear? Good, sir. I think I will not go beyond this. There is a need of some more ordinal numbers and so on are needed later on. I will look at it some other time. I don't want to go more than this. I just want to say uh, I need bare minimum the Jones lemma in many places in topology, and the Jones lemma follows the maximum of choice, and it's equivalent to maximum of choice. Well ordering principle also is equivalent to all these three statements are equivalent to each other. And as I said, Paul Hermos's book, Naive Strategy, is a beautiful book to read everything. Okay? I think that's what I want to do. What I have to do is now get into proving that theorem about compactness. So maybe I should stop here. Okay. Next is to talk about again. uh, I wanted to prove to you last time itself. I said I proved already that for a set is compact if and only if every basic open cover admits a finite subplot. But a set is compact if and only if every sub-basic open cover admits a finite subcover. That result is not too easy as I think it's a wrong result. So the proof in the Simmons next. I will do the proof. Uh, but of course, if I want to put Tignov theorem directly, that's also very good. Tignov theorem is really subtle. Says that uh, any product of compact system, I can have arbitrarily large collection of compact particle spaces, but their product space is going to be compact. Also, an account of that will given to the product topology. It comes out that every product compact. We will take up all these things in the next class. That's enough for now. Uh, that's all from my side. Please, if you have any comments or some questions, you're welcome to ask.
I joined a little late today. I lost first 15, 20 minutes, but I'll catch up later. Yeah.
Actually, we will do much. I continued with my discussion there. I just actually
Yeah.
regretted.
Okay.
I just
John's lemma is the one that I missed, but I'll take a look at it.
I just said what partial order set is once again, and
Right.
what a full element is, and then I said John's lemma, which is a partially ordered set, which every chain has an upper bound, has a maximal element. Uh, and then I didn't prove that. Okay, that proof is
Yeah.
also a little good. I didn't prove that. Then I said axiom twice.
Okay.
You know these things already, and somehow
Yeah.
I
This
didn't.
I followed from here.
So
Okay.
now, all right, sir. That's all for
Okay.
now. And,
Okay.
we'll see you there.
All right. Thank you.
All right.
Thank you, sir.
Hmm.
Take it. Bye.